Next we have Devesh Tiwari from Oak Ridge National Laboratory. Devesh is a research scientist, Technology Integration Group in the National Center for Computational Sciences at Oak Ridge National Laboratory. The title of his talk is SSD Provisioning for Exascale Storage Systems, and thanks to Josh Judd, we know their conclusions already, but please forget that. Devesh, thanks.
Thanks. So I did one thing. I did not have lunch since Josh already said that he agreed with my conclusions. I changed my conclusions. So, sorry, Josh. So, let's see if you still agree. So this work is in collaboration with Sarp, Faye, Saurav, and Josh. So I put their pictures on it so that you can catch them after my talk is over. I do have nicest picture of these guys, but I have not put it there because I was not sure if I put those, they would still continue to work with me. So these are the best pictures that I have. Okay, so SSD, we all know the good, bad, and the ugly, right? So it does give you good performance, lower power consumption and whatnot, more shock resistant. But it has two critical problems, write endurance and high cost per byte. So I would continue to focus on these two things and see if SSDs, we can really build SSDs, a storage system out of these SSDs. Two things is that, one thing is that I will focus mostly on the checkpoints heavily and not the analytics kind of workload. And second thing is, I will also talk about what else can we do with the SSDs. In particular, controllers in SSDs are really getting powerful. They are multi-core controllers. So I will talk about that a little bit too. So let's first focus on write endurance. We all know the write endurance problem of SSD. Let's see, the whole talk is around modeling and simulation, of course, because if you don't have the system, the only way you can get insights about this is by modeling and simulation, right? So, and all the customers, or all the, most of the customers tend to actually over-provision their system. And that's because they have not thought really thoroughly what would be the bottleneck. So they just think over-provisioning is the best solution. So let's think about first write endurance, right? So let's say the projected SSD storage space is 5 to 10 petabytes for HPC storage system. If the building blocks are typically, let's say, 256 gigabytes per SSD, then there would be approximately 20,000 SSDs. And if you look at one of the most recent Samsung SSD, 840 Pro, it says, I will give you 5-year warranty if you write no more than 40 gigabytes per day. Okay? Of course, I have been seeing changes in the data sheet over the years. Before, they used to tell you how much you can write overall. Now they have changed it and said, you have 3-year warranty, you have 5-year warranty. This is how much you can write per day. A simple calculation will tell you that means you can actually write 600 terabytes per day. That's what SSD can experience. Now, there is a critical thing that I want to point out is there's something called write amplification factor. So let's say you wrote X amount of data. Actually, SSD sees more writes. And that's because they have garbage collection going on. They have to erase the block and then replace the whole thing. So amplification factor can be anywhere from 1.1 to 1.8. 1.3 is very typical. This is something that people are actually trying to bring lower. And what does that mean? That means the user can actually write approximately 460 terabytes per day. Okay? That sounds a good number, but let's look at how much checkpointing you do. So if you actually use system level checkpointing, not the user application level, then you would, if you look at the RFP requirements, they would say we checkpoint 50% of the memory. Even if you checkpoint just the 10% of the memory, you will very soon run out of it. So you will actually run into this roadblock. So the first takeaway is that system level checkpointing is, of course, very easy for programmers, but it's really hard if you are planning to use SSD for your checkpoint storage. Okay? you really need to think about either how to reduce the checkpoint size or do user-level application checkpointing. Let's talk about application-level checkpointing. So I think OLCF at OLCF S3D and GTC, if you look at the reports, you'll see that they write approximately 360 terabyte or approximately 400. I think they would still go up in exascale time frame. Darshan has been deployed from Oregon at NERSC and ALCF, and most of the jobs are around, the data movement is around 100 terabyte. It's hard to tell how much is checkpoint, how much is analysis, read and write. But the key point is that you are almost on the verge, and even if you use 1 terabyte of SSD as the building block, you can just write 150 terabyte per day. Of course, you can pay very high, almost 4 times the cost, and get maybe 3 full writes per day. Okay? But still the key takeaway remains the same, that reducing the checkpoint size is the key to elevating SSD write runs. So SSD write runs, of course, device physicists are working, FTL layer is being improved, but there are certain things that we can do as community to think about incremental checkpointing and make it more deployable. So SSDs are good, but if you are trying to use it for checkpointing, probably it's not the best idea. Okay, let's say this problem is not that aggregate, then can we think about where in the system and how much? So typical scenario is, we'll think about SSDs as burst buffers, so compute nodes will write to burst buffer, and burst buffer will actually write to permanent storage. Let me introduce key 2 terms that I will keep talking about next few minutes. One is lambda and another is mu. Lambda is the data production rate. Remember, lambda is not the bandwidth to your burst buffer, it's the production rate, how much data you are generating, how much data is being generated by the simulation. And mu is the bandwidth to the permanent storage PFS storage system. If lambda is greater than mu, then SSD buffer capacity is unbounded. It's a simple queuing model. It tells you, and you can think about it intuitively. You don't have to be an expert in queuing model to figure this out. If your drain rate is lower than actually your influx, then no matter how much you provision for SSD, it's not going to work. So we cannot say we have a lot of SSD capacity and that solves the problem. If your file system is really slow at the back end, no matter how big SSD, how big your space is, it's not going to solve the problem. Second thing is, PFS bandwidth is still critical, and I will explain in a little bit more detail why is so. Let me define a new metric, utilization, which is the production rate divided by the achievable PFS bandwidth. So you may have 10 terabytes of achievable PFS bandwidth, but let's say you are only getting 100 gigabytes. And your production rate is maybe a couple of gigabytes. So that is how I define utilization. Again, lambda is not same as the SSD bandwidth. Okay. So on the left-hand side, again, I have ignored all the modeling, all the simulation part. I'm just showing you the cherry-picked results. On the left-hand side, it just shows, it's like a queuing model, how many customers are in the waiting queue. So if you look at the left-hand side, that tells you how many customers are in the waiting queue in some sense, or how many SSD burst, simulation burst you have not accounted for. As the utilization grows, the overall capacity that you need increases exponentially. Now, the second figure may not look like exponential because that's log axis and left one is not on the log axis. The reason for log axis is I want to tell if output size, let's say every time you have 20 terabytes, you output 20 terabytes at one cycle, at one time, then maybe if you will have approximately 50 such output sizes which you will need to hold because you are waiting because the draining system is really slow. And that comes out that you will need approximately 1,000 terabytes, 1 petabyte of storage space. That is if your utilization is very high. If it's low, then probably 10 terabyte is good enough. I can increase the output size, which I will increase, but before I do that, the queuing model clearly suggests that average queue size is actually increasing exponentially as the increase in utilization. So if your PFS bandwidth is really low and you are producing at a faster rate, such that they are very close, then it's not about what is the SSD bandwidth, it's about how much capacity you need, and your capacity will keep growing. And I changed that to 100 terabyte and 200 terabyte, and of course you need more space. And I think approximately 1 to 5 petabytes. But if you are around 80% utilization, you are good with 1 to maybe 3 petabytes of total storage. That is just about the storage space. But before I move on to bandwidth and so on, I want to point out that this is actually a model which causes excessive data movement. And we cannot keep doing that because the Exascale report, and some of it I think Sai also touched upon, excessive data movement, the data movement cost would be as much as your computation. So getting your data block from cache to your, from memory to your cache in register will be same as doing a floating point operation. So think about going even further. So this is, I'm not sure if we can continue to think in this term. We need to think of two separate boxes. One is SSD-based storage, and one is hard disk. And users will need to actually figure out, we will need to, since we are incurring different costs for actually provisioning them, we need to charge them. And that's just my personal opinion, or whatever I say is my personal opinion. I think we will need to think about what we will need to, how we will need to charge users based on how much they write to SSD and how much they write to permanent storage system, because those two are not the same. Finally, what is the bandwidth that we are talking about, and why is it that we really need a good storage system? And I will explain very quickly why is that so. Think of checkpointing and restoring as your reducing your waste work, right? So if you take checkpoints very often, of course, we are going to you are going to actually experience very less amount of waste work. But if you take checkpoints very periodically, you will waste a lot of work, right? So tendency is that you will actually hit somewhere in the middle. Now, this one shows, this figure shows the efficiency, and efficiency, when I say efficiency, I mean how much waste work is happening. Okay, so if I say 67%, which is for the, let's say, petascale system, 1 terabyte per second, again, this is just from the simulation, you have 67%. If you want to achieve the same efficiency, you have to provision your, whatever your next level storage system to be around 20 terabytes per second. So you cannot just think, oh, I scaled my system by 5x, the compute system, I will scale my storage also by 5x. It has to be more than 5x. And that's because of that's the interplay between lost work and checkpointing cost. It just shows, for different terabyte per seconds, how much efficiency you are getting. Storage system bandwidth actually determines the overall efficiency. So we need to also, this is why it's really critical that we need to provision it properly. Now let's look into the cost side of it, right? And again, I will present some numbers. They are rough numbers. They are not unofficial or official quotes from any of the companies. But these are the numbers. These are the actually trends for SSD. Write throughput, MB per second per dollar. Okay, so I like to think in per dollar aspect. If you see, SSD is actually over the years increasing pretty fast. The current SSD is, hard drives is very low. Same goes for the read. And again, these are not random, these are just sequential parts, okay? The problem is the gigabytes per dollar, okay? That SSD is, pretty high. Actually, it is more higher than what is shown here. If you go to someone, they will tell you that they can offer much cheaper hard drive. So I think a factor is here, maybe 1.5, but in next model, I will show the factor is 4. So how do you build a whole storage system? It's very complex to account for everything, I/O controllers, JBOD I/O module, enclosures, power and cooling, RAID and firmware cost. So I'm just going to focus on hard disk and SSD cost and I/O controllers, just for simplicity. So, and I have tried to give hard drive as much advantage as possible. So let's say 4 terabytes, $500, performance is 200 megabytes per second, and SSD is only 500 megabytes per second. And a pair of mid-scale controller is 8 gigabytes per second for an 8K cost. Each shelf can actually hold 60 drives, and as you can see, 40 hard disks are enough to saturate one pair of controller. And for SSDs, this number is much lower. This number is just 16 SSDs. So that means if you are to build a bandwidth-oriented system, you will need to buy more controllers, and that's the cost that you should also focus on. But if you are planning to just build a high-capacity system, forget about SSDs, of course. GB per dollar cost for SSD is too low to beat anything. Okay? But if you're building a bandwidth-oriented system, then there is a typo here. It should be for SSD. Let's talk about 10 terabytes per system per second. That means you need 1280 controllers, pair of controllers. That's approximately $10 million. And then hard disk-based systems, you will have 40 hard disks per pair of controllers. So I just multiplied by that. And I'm using just 1 terabyte because this is a bandwidth-oriented system. So I want to keep the cost low. You will get another $10 million. So the total cost is $20 million, but the capacity is 50 petabytes. If you do the same thing for SSD, there is a typo here. It should not be 40 in SSD. It should be 16. That's correct in the next line. So if you just do 16 and $250, you will get actually just 5 million. Of course, the bad news is your capacity is only 5 petabytes, and the cost is 15 million. But the majority of the cost is actually also coming from I/O controllers, which people used to ignore. Of course, it's not a big deal for enterprise community where they have actually local disks. But I think we need to think about how fast these SSDs will actually saturate controllers. There is our ongoing work where we are trying to characterize the workloads to figure out not just on checkpointing, but on actually how much is the random read-write, what is the request size, and then how do we provision. Luster and RAID overhead, that's also part of that. The last thing that I want to talk about is what else can SSDs do for us. So of course SSDs are costly, but there is one more thing that I mentioned initially, that they have multi-controllers. So one thing that we propose, and this, you can read the paper in detail if you're interested. Traditionally, people do data analysis on the offline cluster. So they store everything on the PFS, then read it back, and do the analysis. But energy cost for data movement at exascale is likely to be of the same order of computation. So what we are proposing is sort of in situ, but it's on the storage controller itself. So SSDs have these controllers, and we developed a prototype which I will show, where you can actually embed your data analysis in that controller and do the analysis. The only problem is you need to be sure that you finish the analysis before next burst of data comes in. And also, there is something called I define a staging ratio, which means how many compute nodes will send their data to one SSD. Okay? There is complex math. I'm just going to skip that. I don't know if this will play here. Let me see if, I think it's playing. Okay, so it just shows they send the data. If there's too much data, then you can, too little data, then you can do a lot of analysis. And if there is too much data, then you can only do a bit of analysis. See, it will finish quickly. You have to finish quickly. You cannot do a lot of analysis. If I go back, then probably it would become more clear. Let's see. See, if it's small, if the data output was very small, then you can do a lot of analysis. And actually, we've built a prototype, and we also did modeling and simulation. So let me show some of it. Depending on what is the data production rate of the analysis, of the simulation, and what is the compute intensity of a particular analysis, I'm just going to skip over these results. You will figure out what analysis kernels can be embedded in the FTL of SSD and what cannot be. If you do all that, you will actually, I will just cover the findings. We found that most data analysis kernels actually can be placed on SSD controllers. without degrading the simulation performance. You just have to put them in FTL, and they will execute as if you execute the garbage collection routine. And additional SSDs are not actually required for supporting in situ data analysis, so there are enough of them if you just have, except few applications which are very busty. The prototype is built on OpenSSD platform. It's a very slow controller, but it still does the job for us to just hard code FTL and get the analysis running. There are more details, implementation details in the paper. And I think that would be it. So that's it. Was it too fast, too slow?
Good.
Okay.
Questions?
Yeah.
Classic model, all the nodes are writing to the parallel IO. In yours, you're showing that all the nodes are writing into one or two nodes.
Yeah.
And that will create a bottleneck right there when you're in the middle of the simulations.
So parallel I/O, yes, that part I agree. If they are writing just to, so our model says, okay, if you have 10 compute nodes, they're just writing to one. All of them are designated where to write. Right. So you cannot do, or at least we couldn't do across these if, let's say you have to do a reduce. So you will need to have another layer on these SSDs so that they can go ahead and do the reduce operation.